Good afternoon, everyone, and welcome to the Texas Atmospheric and Space Research presentation. During these 2 fantastic weeks, we collaborated with our mentors, Professor Nick Pugh and Bob Twiggs, Laura Tomlin, and Melissa Pore, to launch high-altitude balloons that aid in the understanding of both the Earth's atmosphere and space. We're very excited to share our findings, so without further ado, let's get started. During this time, I worked alongside many talented individuals to design and launch our high-altitude balloon. It gives me great pleasure to introduce the TASR team, pictured with Dan Tanny, a NASA astronaut. From left to right, on the top row, we have Leah Franklin, Tammy Zhang, Viviana Novelo, Robert Twiggs, Dan Tanny, Nick Pugh, Giuliana Trevino, and Ariel Reyna. On the bottom row, left to right, we have Melissa Pore, Hailee Gooden, Marissa Tucker, Victoria Mascorro, me, Londyn Franklin, and Janelly Perez.
What is high-altitude ballooning and why is it important? Well, scientists have been exploring the Earth's surface since the beginning of time, and now space exploration is becoming more advanced and common. However, the one area that often gets left out of the loop is the Earth's atmosphere, which is the layer of gas between Earth and space. And high-altitude balloons, HABs, are perfect for studying this. They can reach anywhere from 60 to 100,000 feet above the initial launch altitude, which is right around the Earth's stratosphere. This means they are reaching much higher altitudes than the average airplane. To collect data, the balloons are equipped with a payload containing a variety of sensors to measure pressure, temperature, humidity, altitude, CO2, and O2 concentration, among other things. And sometimes they are also equipped with a camera. It also has a GPS that allows us to retrieve the payload once the data is collected. All the data collected by the balloon can then be analyzed, made into correlation graphs, and compared with other balloon flight data to better understand our Earth's atmosphere. On top of all that, high-altitude balloons are relatively cheap at around $100 each, which costs a fraction of the amount it takes to launch a satellite into space. High-altitude balloons are extremely accessible and versatile, making these balloons the most efficient way to study the Earth's atmosphere and everything about it. Now we're going to share a little bit more about the TASR team.
Hi again, my name is Londyn, and I was the mission manager at the launch site. I communicated with our communication leader of events occurring at the launch site, and I gave clearance for the balloon to be launched.
Hi, I'm Hailee, and I was the materials and data recorder for the launch site team. I made sure that all the necessary materials were accounted for and at the right location. I also recorded vital information, such as timestamps of the balloon launch and cut commands.
Hi, my name's Ariel Reyna, and I was the launch operator for our team. So my job was to protect the balloon from any hazards that would pop it and ruin our experiment. And another part of my job was to conclude the optimal time and conditions to launch the balloon without any problems.
Next, we have the chase team. My name is Leah Franklin. I was a mission manager for the entire chase team. I communicated with the communication leader of events occurring within the chase vehicle, and I oversaw the antenna operations.
Hello, my name is Marissa Tucker, and I was safety and procedures. I ensured everyone was safe and following all rules, and I determined whether an area was safe for retrieving the balloon.
So my name is Janelly Perez. I was the antenna operator, and what I did was pinpoint the location of predicted payload landing and observe the data being received by balloon to aid in finding it.
Hi, my name is Tammy Zhang, and I was the weather monitor and antenna operator for the chase team. As the weather monitor, it was my job to check wind patterns, which helped determine the balloon's flight path, and also check the UV index to make sure that it was actually safe to fly our balloon that day. Also, as the antenna operator, I used the antenna to receive data from the payload.
Lastly, we had ground control team. Starting off with me, my name is Giuliana, and I was part of the communications. I created a reliable form of communication between groups and made sure important information was passed between the groups.
Hi, my name is Viviana, and I worked in data analyzation for the project. The main part of my job was to analyze the data collected from the payload, such as the coordinates, altitude, temperature, and humidity. For the coordinates, I would chart the location on a map in order to visualize the path the balloon took. As for the other data points, I would graph the information on Google Sheets and Excel in order to present the findings accurately. Afterwards, I would share the created items with the rest of the team in order to explain it equally.
Hello, my name is Victoria Mascorro, and I was the data collector for our ground control team. Now, I specifically was able to read and analyze all the data that was being transmitted from our payload, specifically the latitude and longitude that was then I related to the data analyzer. And then I was able to inform and communicate many of the major problems that were coming with our programming. So I made sure to take a heads up as well as stop anything that may have been tracked when following the balloon.
In preparation for our launch, we used a balloon, payload, helium, and other materials to construct and measure the high-altitude balloon. In addition, we We use scientific weights and a weighing instrument to find the balloon's neutral buoyancy point and ensure that the balloon can support the weight of the payload. The launch team used communication devices to communicate with the other teams and a journal to note the time of launch, the initial direction of the balloon, and other important events and information. The operations team used laptops to predict the flight path of the balloon and track the live coordinates received from a high-altitude balloon. They then transferred this information to the chase team through communication devices. The chase team used antennas and communication devices to receive information about the location of the payload.
Following our materials, this is our most important material. We have our payload. Our payload is a motherboard, and it consists of two sensors, one that senses pressure, temperature, and humidity. As you'll see, it connects to the red wire. Then we have the second sensor, which at the bottom connected to the black wire. It senses carbon dioxide, hydrogen, methane, and other volatile gases in the atmosphere. Next to that, we have the blue component you see on the board is our GPS antenna, the GPS electronics, and then the yellow and white component you see on the board is our GPS antenna. Then to the left, beneath our GPS electronics, we have our radio antenna, which is the red component you see. And connected to that, we have the radio antenna jack, which, senses everything. It's the main antenna. Next to that, we have the Chow ZPU. And then we have our battery underneath the board to power it all.
One of the best factors of learning new things is being able to share with others. Here in this collaboration page, we have our team sharing with the Eclipse team about our new findings. And here we have pictures of us on roller coasters and Six Flags, demonstrating altitude and humidity on a ZQ, as well as a tethered launch and sharing our experiences with it.
Important aspects that we discussed with other groups were the procedures. First, we measured out the payload and added around 30 grams for a positive lift. Next, we measured out the length of string for how high we want our balloon to go. Then we filled our balloon with helium with around 32 inches in the balloon's diameter. Then we used lab weights in a Ziploc bag clipped onto the balloon's string to measure the balloon's weight. Then, once the balloon was neutrally buoyant and not going up or down, and weighed at least 100 or more grams than the payload's net weight, we connected the payload to the balloon.
On the payload and test it to make sure that it is sending the correct data. To do this, you can check the time given on the payload with the real time that you have from a clock or a phone to make sure that the data is synced up. Next, you have to raise the balloon up to your preferred height and hold it in place for about 60 seconds so that it can collect the data. So after you record and collect the data during your flight, after you finish, you bring the balloon back down and turn off the payload. Untethered launch, measure out around 3 feet of string to hold the payload and create a message in case it goes missing. So this would contain your contact information and your name and what your project is about. And ensure the GPS system is functioning properly and consistently, and predict its flight using a website so that you can find it, and proceed with the rest of these steps.
Following the tethered procedure launch, what is a tethered launch and why did we do it? This tethered launch was a balloon with a rope attached that gave us easy retrieval, and it had an SD card inside for data, and no GPS was necessary. Why did we do this? It was an opportunity to teach others and give us experience for our future launches.
Our Trial 1 free launch was on July 12, 2023 at 15:09, where the temperature was 103 degrees Fahrenheit with a 9-mile-per-hour wind heading north. The payload weight was 180 grams, and the neutral buoyancy weight of the balloon was 195.5 grams. 22 minutes after the initial launch time of the balloon, the first cut-down command was sent to the payload. However, when there was no confirmation that the cut-down command was received, a second cut-down command was sent at 15:37. Shortly after the cut-down command was sent, the operation team stopped receiving data from the payload. The chase team continued to attempt to locate the payload based on the last received coordinations. Unfortunately, after no success in locating the payload, chase operation was aborted at 16:03.
During this trial, we encountered many unfamiliar situations, which allowed us to be better prepared for our next launch. We were able to redesign our pre-launch plan and develop an essential materials list to have a more efficient launch. We also relocated our ground team location due to a Wi-Fi connection issue. Although we had to redesign many aspects of our launch, we also discovered many things that worked efficiently, like our antennas. This experience allowed us to gain knowledge and experience to improve on our future launches.
For this next slide, I will explain the maps we used for the first free launch trial. On the left, we have the predicted flight path made using stratoflights. I inputted the launch time, altitude, and coordinates to produce this result. This helped us determine the direction the balloon would initially fly in and gave us a general area to send our chase team to. On the right, we have the actual flight path the balloon took. In order to map it, I inputted the latitude and longitude I received from the payload into Google Sheets and used the extension Geocode by Awesome Table to visualize it. We see that for the most part, the actual flight matched the predicted flight as they both flew northeast initially. However, we saw that the balloon continued on in that direction and didn't reach a high enough altitude to turn back as predicted. This might have been because the balloon did not have enough helium. Now we have the charts graphed with the data extracted from the payload. On the left, the graph displays an opposing relationship between temperature and humidity. As the balloon reached higher altitudes, we saw that the temperature would increase and the humidity would decrease. The same relationship can be seen on the graphs on the right. As soon as the balloon launched from the initial 260 meters, data regarding the humidity and temperature in regards to the altitude were collected.
Now we have trial one pictures. So on the first, we have the ground team setup as well as the antenna. The antenna was connected to a tripod so that ground team could keep an updated and refreshed system of the balloon to know where exactly it was, and of course to update chase team. With that, the board and the tree of script, specifically the board was found inside of the payload, and it was able to then track the GPS, ethanol, CO2, and H2 emissions, as well as other things. But the tree of script was a more in-depth look at to what it was exactly tracking. So if the GPS was being updated every 20 seconds to about a minute, the ethanol and CO2 would also be updated. And finally, the Bluetooth terminal as well as the ping for it was for chase team's location of it. So they had their own handheld Bluetooth connection to a phone that then would tell them where exactly the balloon was, as well as the other things that ground team was also monitoring. Now continuing on with other trial.
So for the second trial, the payload and balloon was launched at around 2:35, with the payload having a weight of 140.8 grams. After 5 minutes, the launch team lost visual on the balloon, and during the launch, the chase team stopped receiving operation data at 2:47, with the last chase ping being at 3:17. And finally, at 2:45, the cutdown command was sent because of discontinued data. So due to a modification of the code before launch, we were unable to test the connection between the payload and our receiving computer. And this resulted in a system failure during the balloon flight that caused a malfunction in receiving the payload's location. Because the live GPS location was not available, we decided to issue a cutdown command earlier than expected. And no confirmation of cutdown was received, so we were unsuccessful in finding our payload. Despite these difficulties, though, our prior trial experience enabled us to plan well and work as a cohesive team.
Following the previous slide, you can see pictures taken from Trial 2. They encompass different stages of our launching. On the left, you can see how all the teams met up first on the ground to prepare the balloon for launch. Across from it on the right are our ground team when we first realized we weren't receiving coordinates from the balloon. You can get a closer look into the equipment we were using on the bottom left. Across from that are our groups in their respective areas. We have our launch team on their way to the roof and the chase team observing how to position the antenna in the best way to receive pings. Overall, this launch was a great learning experience, so here's what we learned.
We learned that in order to make the most successful project with a lot of people working on it, such as our group of 10, it is imperative to create procedures that everyone must follow before, during, and after the project. It's also always better to have more than one person check on the predictions of our flight so we can get the most accurate results of where the balloon will be landing and make sure the data that was put into the predicted flight simulator was correct. While we were doing our initial research, we understood that breaking up the teams into smaller subsections allows us to be the most organized and have specific people check up on what exactly their teammates are doing and create goals that can be accomplished. Now, my teammate Victoria will tell us the rest.
Continuing on from what we learned, we understood that there were going to be many problems that were going to occur throughout the ballooning experiment, but we understood that we had to work through them and communicate with each other throughout it all to solve them and to understand specifically what the problem was. Now, with that, we were able to make sure that every aspect of the project, including the procedure of it, was clarified before the launch so that not only could it run smoother, we could spend more or less time on things that needed to be fixed, as well as just making sure that everything had someone designated to. So which, as well as with the roles, we were able to break them down a bit more specified, as well as a bit easier and flexible to what everyone needed to do, so that no one could be left out, and that everything was clearly stated to make sure that everyone had the opportunity to contribute to the project. Now moving on to what specifically we can apply.
We applied our learning of procedures to how we broke down certain instructions. Because we understood the procedures had to be as clear as possible, we applied what we learned into creating a list of the things we had to do in preparation for the launch. This also helped for the future launches because if something went wrong in a previous landing, we could know which step wasn't taken correctly and fix it for the next one. Because we wanted to maintain validity when it came to possible predictions of the landing, we made sure that we had people check the path or even put in their own in the computer to make sure the results looked right and were similar to one another. We also applied that to other aspects, such as our data analysis and comparison of certain data, such as temperature versus humidity. Since we understood that our team could divide and conquer with different tasks, we split our entire team up into groups and made a clear list of the objectives that each team had relative to the balloon launch. As we did multiple trials, we continued to utilize the same team objectives for the launch. We also had a communication system for certain individuals to make sure every team is ready and are doing their specified tasks correctly. During the trials and tentative launch of the balloons, we clarified each step that was being done and made sure that every member of each team understood what was going on so everyone had the chance to accomplish their goals effectively. For our balloon launch, the teams were debriefed and were given time to ask questions. This also occurred after the team was analyzing the data results collected from the balloon. The results that we split into were purposeful so everyone could be involved and people would pay attention to specifically their task, which would prevent mishaps from occurring. The role breakdown allows every person to pay attention to the smallest details of their job and be successful in what they do, because if all 10 of us were focusing on one thing for the launch, there could be a possibility of a future failure since we weren't observing other aspects of the project.
These are our references. With that, our presentation is now concluded.
We would like to thank the Center of Space Research, especially Miss Selena and Miss Margaret, for their hard work and dedication to this program. We would also like to thank our mentor, Professor Bob Twiggs and Nick Pugh, for their time and expertise, alongside Melissa Pore and Laura Tomlin for their dedication to the program and hard work. At this time, we will take any questions or comments.